I call this the "What are you doing here?" lesson. Like, you guys know when you're gonna laugh at this, but I've been watching episodes of The Flash. I don't know if anyone's keen on everything. Hey, here. So I've been watching it, and one of the big things in that TV series and in many other like popular things is like there's a character and they're masked, right? And their voice is like disguised, and a big plot point is who is that character, and then you find out who it is, and there's a "You? Like, what are you doing here moment? Like, you're not supposed to, I thought you were dead," or "I thought you were so-and-so's dad," and then, you know, it's all a bit confusing, right? Mathematics, surprisingly, has lots of moments like that. Today, we're going to do two of them, where we're going to look at a concept, and we're going to start digging, and you're going to find something where it's like, what is this doing here? This is not what I expected to see, okay? So this is going to happen to us twice. I'm going to show you what I mean. Okay, so you might like to write this underneath your vacant heading at the moment. You've done, for the most part, you've done series and sequences already, okay? Now, the main kinds of series and sequences you focus on, what are the two kinds? There are two varieties. APs, which grow with a common difference, and GPs, which grow with a common ratio. Good. Then you've got ratios, or rather sequences, that don't follow either of those patterns, right? So this is neither an AP nor a GP. It is in fact the, come on guys, I know it's the afternoon, you recognize this. It's the Fibonacci sequence, 13 and then 21 and then 34. The Fibonacci sequence, it's a famous sequence for a number of reasons, okay? Now, one of the reasons why in 2 unit we don't focus on series like these is because they're actually much harder to work with. Even though the building blocks of this are very simple, what is the way that you construct this series? What rule would you explain to someone to get the next number? You'd say, well, if you want the next number, you just take the two previous ones, yes? And then if you want the number after that, you just take the two previous ones. So we call this a recursive definition. A recursive definition. It's a definition that is based on itself, right? So you've got to go all the way back through. Now, there is actually a formula for this series. I want you to write it down with me. For the nth Fibonacci number, okay? Now, this sequence is quintessentially about natural numbers. Think back to the beginning of complex numbers. We said natural numbers, they're just 1, 2, 3, 4, 5, right? That's the kind of building blocks that you find in this. Let me show you what the formula for the Fibonacci sequence is, and you may be a little surprised, okay? Bear with me. I have to introduce some new notation. Did I remember it right? I did. Okay, so what you're looking at here is a formula for the nth Fibonacci number. All you have to do is put in n equals 1, 2, 3, 4, 100, whatever you like. Where this Greek letter, does anyone know what the Greek letter is, by the way? Phi. It's phi, okay? Where phi is this particular number over here. This number is very famous. It's about 1.6. Does anyone know what it is? This number here is the golden ratio, okay? The golden ratio is really important. You can go on Wikipedia and find out all about it, and your mind will promptly explode. I don't have time to explain it now, but my point is that this sequence is about natural numbers. Yes? It's about natural numbers. And in order to generate this sequence with natural numbers, for some reason, we have to appeal to irrational numbers, right? Not even like rational numbers. They'd be weird enough because there are no rational numbers here. We go all the way down the rabbit hole and you've got square roots in there. What's up with that? Okay? So this is what I mean by, this is just a very small example of, what are you doing here? Right? Like, this is what I was expecting, and you dig underneath the surface and this is what you find. Okay? So that's weird, and I'm going to show that to you in 2 ways with complex numbers. Okay? So